In this video, we are looking at rational functions and add behavior. And I want us to start by addressing some points that we need to take into consideration as we do this. So the first one, the add behavior of a graph of a function is how the graph behaves as it approaches positive and negative infinity. The next one, the add behavior can be modeled with a horizontal line, an oblique line, or a polynomial. The add behavior of function only describes the behavior of the function when x approaches negative or positive infinity. So note that. And that looks like point number one. Knowing how the behavior or the function is shaped for large values of x does not tell you how the function behaves for smaller values of x. For this reason, the statement that a function cannot close an asymptote is not valid for horizontal and vertical asymptotes. Remember, this only applies for large values of x when we talk about what's happening with the asymptotes here. So the add behavior of a polynomial can be modeled in three ways. One, the add behavior could be a horizontal asymptote. So we are saying as the graph approaches infinity, it's going to approach an asymptote, a horizontal line. When the degree of the numerator is less than or equal to the degree of the denominator, that's when we are going to have a horizontal asymptote. So you can know it by comparing the degree. Okay, B, when the degree of the numerator is 1 more than the degree of the denominator, the rational function will have an oblique asymptote. This is the same as a slanted asymptote. So in this case, no horizontal asymptote. Next one, it says asymptotic to a polynomial. It's going to behave like a polynomial. So when the degree of the numerator is at least 2 or more than the degree of the denominator, the rational function will behave like a polynomial. Okay, so same add behavior as a polynomial. That's what we mean by that. So here we are going to consider two cases. Case 1a, that's when the degree of the numerator is greater than the degree of the denominator. For example, in this case, you see the numerator has a degree of 4, denominator has a degree of 3. In order to determine whether we have a horizontal asymptote, we must find limits as x approaches infinity, that's negative and positive. And before I begin, I need to find the dominating terms, and I'm going to ignore everything else. So I'm going to write them down. So I have x to the power 4, and this is divided by 2x cubed. And I can further simplify this to get x over 2. So when I get this, I'm going to evaluate what happens to f of x. So I'm going to do limit as x approaches negative infinity, and I want to see what's going to happen to f of x. And I'm also going to do the same on the right hand side. I'm going to do limit as x approaches positive infinity, what's going to happen to f of x. And to do this, I'm going to consider the function I have here. If I have x, y is equals to x over 2, and I'm going to plug in, instead of x, I'm going to plug in a very big number, a very big negative number. And then I'm going to divide it by 2. And if I do this, a very big number, because I'm approaching negative infinity, I'm still going to get a negative big number. So that means my graph is going to be approaching negative infinity. The values of y are going to be approaching negative infinity. Over here, I could do the same, take my simplified form, x over 2, and as I approach positive infinity, so I'm thinking of a very big number, and I divide it by 2, if I divide that number by 2, it's not going to make a difference. A very big number. I'm approaching infinity. So that means the y values are going to be very big. So they're going to be approaching positive infinity. So what is the conclusion from this? Because on both sides I'm approaching infinity, I know that infinity is not a specific number. So what this means is that this function does not have a horizontal asymptote. It does not have a horizontal asymptote. And specifically, because the degree of the numerator is 1 more than the degree of the numerator, which is 3, I'm going to have a slanted asymptote. So whenever the degree of the top is more than the degree of the denominator, there is no horizontal asymptote. So you can see the reason here. We are approaching infinity from both sides. Now, when I graph the function we just described, I want you to see how it looks like. And this is a function in red. And you can see it's crossing the graph initially here, but as we get large values of x, it's just going to approach the asymptote. The dashed line is the asymptote. And over here, and you see we don't have horizontal asymptote. Instead of it's oblique or a slanted one. And over here, I graphed the function y is equals to x of 2. This is the one I graphed over here. And see, these two, my function and this one, they have the same edge behavior. As you approach infinity, the simplified form, you see the graph approaches positive infinity and negative infinity. Here it's going down, it's going up. The same case you see happening right here, same edge behavior. So here we look at another example. This is case 1b, and still the degree of the numerator is greater than the degree of the denominator. But I want you to see here the degree of numerator is 3, denominator is 1. So it's more than 2 degrees. So 2 degrees higher for the numerator. So when I I'm going to identify the dominating terms, and these are the dominating terms right here. So when I simplify, this is what I get, x squared. So now, that's what I get when I simplify. Now, let me use limits to determine the edge behavior. And I'm going to write here, limit as x approaches negative infinity. Since I have x squared, if I plug in a very big number, square it, I'm going to get a very big number. And actually, in this case, the number is still going to be squared and positive. So I'm going to write f of x is going to approach positive infinity. And I'm going to, even when I do it on the other side, limit as x approaches positive infinity. Since the number is going to be squared, it's a very big number squared, that means the y values are still going to be approaching infinity. And this means that, because I know infinity is not a specific number, it means I do not have a horizontal asymptote. So I can come here and remember a horizontal asymptote does not exist. And remember, it's the same thing if the degree of the top is more than the degree of the bottom. But I want to add one here. So specifically, the degree of the numerator, 3, is greater than the degree of the numerator. It's more than 2. So in this case, even you're not going to have a slanted asymptote. So when I graph the two functions, I want you to see how my function looks like here. And I graphed the simplified form that's when I consider the dominating terms. And you see they have the same edge behavior. So this polynomial here, this rational function here, behaves like this polynomial. The edge behavior is the same. You can see to the right, it's going up. To the right, this is going up. Sorry, I mean this is to the left, going up. And I see to the left, going up. To the right, it's going up, going up. So they have the same add behavior. Okay, now here let's look at some questions, and we are considering case number 1. So the first one here, let the function f of x is given by that has the same add behavior as. So that's a question, and I need to select from this the choices I have. So how do I do this? First of all, I'm going to identify the dominating terms. In the numerator, I see negative 3x to power 5. And what do I have in the denominator? I have 4x squared, and it's all positive. So when I simplify that, I get negative 3/4 x to power 3. Okay, so I'm looking for odd degree because I see the degree is on, and I'm looking for a leading coefficient which is negative. So odd degree and leading coefficient negative. So which one meets the criteria? So I'm looking for negative. So and leading and degree odd, and I see the first one is the same. Look at the first one. The first one will behave the same way. And remember, the leading coefficient doesn't have to be the same number. I'm just looking for negative. This one happens to be the same. And let me look whether there is another one. Look at this one. This one is odd and negative. So those two will work. And if I look at number 2, this 2 is positive. This 2 is positive. The leading coefficient is positive, and the degree here is even. I just need odd and a negative leading coefficient. So 1 and 3 will apply here. Okay, now let's go to this other one. Here we are given a polynomial, and we want to see which one has the same add behavior. So to be able to do that, and see here, I made this negative. So this is me who made this negative. So I'm going to consider what I'm given. So I need to focus on that, the leading coefficient and the degree. I see it's odd. And now I just need to look at each of these and see which one I can simplify, ignore everything else. So let me highlight the dominating terms. So that's numerator and denominator. If I subtract those ones, I see the degree, the higher degree is in the denominator, so that doesn't work. I go to the next one. I see the higher degree is in the numerator, and I see the difference here is 3. So if I simplified that, and I have negative 8x to power 8 divided by 7x to power 5. If I simplify this, I get negative 8 over 7 x cubed. And from here, I see that this one actually has the same behavior. But let me check just in case there is more with the others. The next one, I see the same degree. So that's R. The bottom one, I see it's x cubed. Oh, but that's not the highest exponent. Highest exponent is actually x to power 6. If I simplify, it's going to be x power 4. So that one is I just need to simplify and see which one has an odd degree, like the one I'm given here, and negative leading coefficient. So the answer is B. So here we have case number 2, where the degree of the numerator equal degree of the denominator. So again here, identify the dominating terms and simplify. So I have f of x. F of x is going to be equal to 4x squared. And I'm dividing by 2x squared. And when I simplify that, I'm going to get 2. Now let me find limits. So I need to find limit as x approaches negative infinity. So I'm going to figure out what is f of x. And then I'm going to find the limit as x approaches negative, positive infinity, and determine what the values of y approach. And I have 2, so if I have, I'll use my simplified form. If I have 4, so y is equals to, and I'm going to plug in a negative big number squared, and I divide by 2, negative big number, and I square it. See this one, these 2 will cancel out, the big will cancel out, I'm left with 2. And the same thing will happen here. So y is equals to 4. Now I'm going to positive infinity, a very big positive number squared. And I do the same, 2, and I do big squared. And again, I'm going to get 2. And you can see I'm getting the head behavior is approaching 2 on both sides. So that means the horizontal asymptote is going to be equal to the ratio of the reading terms. So whenever the degrees are the same, these 2 numbers here, the leading terms for numerator and denominator will give you the asymptote. In this case, it's y is equals to 2. Always remember to write it as an equation. Now, graphing this function, you can see how it looks like. You can see it's approaching the dashed line, which is the asymptote y is equals to 2. Now let's do case number 3. Now here, the degree of, here there is a typo, the degree of the numerator is less than degree of the denominator. And you can see this is 2, the other one is 3. So again, I'm going to identify here the reading or dominating terms. So I have 2x squared, and I'm dividing that by 2x to power 5. So what am I going to get? So I'm going to get a simplified form of 1 over x cubed. Okay, now I'm going to find limits of the head behavior of both sides. So I'm going to find the limit as x approaches negative infinity. So what happens to f of x? What are the values of y going to approach? And I'm going to do the same on the other side. As x approaches positive infinity, f of x approaches what? Okay, so here, if I take 1 over a big negative number cubed, see, I'm dividing by a very big number. 1 divided by a very big number is going to, and the number is not constant. As I get bigger numbers and bigger numbers, it's going to approach negative. It's going to approach 0, going to get very small. Again here, y values, what will happen to them as I plug in very big positive numbers cubed. This is going to be a very big number. So you're dividing 1 by a very big number. So the answer is going to be approximately 0. So f of x is going to approach 0. See, I'm approaching 0 from both sides. That means the horizontal asymptote is just going to be y is equals to 0. And I have it here in the conclusion. If the degree of the numerator is, let me fix this, is less than the degree of the denominator, a horizontal asymptote exists and is equal to y is equals to 0. And if I graph it, you can see this is the function here, and the asymptote is the dashed line here, y is equals to 0. See, for larger values of x, is going to get closer and closer to that line.